Hi everyone, today we're doing section 9.4, part 4 on direct and limit comparison test. So these should look really familiar to you because we did direct and limit comparison test with improper integrals back in section 8.3, part 3, and this is going to be very similar. So the direct comparison test is first. It says if a sub n is greater than 0 and b sub n are greater than 0. So notice, we've got positive sequences. So start there and look whenever you're looking to use the test, make sure your sequence is always positive. If it's not, move on to another test. If the series from n equals 1 to infinity of b sub n converges and 0 is less than or equal to a sub n is less than or equal to b sub n, then you know that the series from 1 to infinity of a sub n will also converge by direct comparison test. So notice this is saying if you have a series and the bigger one converges, then you know the smaller one's going to converge as well. Let's take a look at the second part. It says if you have a series from n equals 1 to infinity of a sub n and you find that it diverges, so look at that, the smaller one's going to diverge, well, then we can conclude that that bigger one also will diverge. Get a pin. Also will diverge by dct. And I'm going to draw a little picture here. So we had done this back when we were doing improper integrals. So kind of picture your sequences here. They don't necessarily have to look like this, but here we're saying that a sub n is always going to be less than b sub n, whatever it looks like. So we're saying if the bigger one converges, well then the smaller one has to converge as well. And then with a sub n, if that one diverges, well then b sub n, the bigger one's going to have to diverge as well. Notice that those are the only directions that it works. So if you were to find that b sub n diverges, well that tells me nothing about a sub n. And if you find a sub n converges, that tells me nothing about b sub n. So let's take a look at some examples where it might be beneficial to use this test. So here, I need to determine whether this series is going to converge or diverge. And I'm looking at this and I'm saying I'm not going to use a comparison test at all because I notice right away if I take the limit as n approaches infinity of n cubed over n cubed plus 1, that limit is just equal to 1. And we know from a prior test that since this is not equal to 0, that this series will diverge by the nth term test. So remember, that's always your first test. That's always your first spot check, because if it's going to fail that nth term test, you're all done. You know it diverges. But now let's change it up a little bit. So notice here I have the same series except for that numerator is now a 1 instead of an n cubed. So now my spot check, if I take that limit as n approaches infinity of a sub n, I will indeed have a 0. So it might converge. So now I'm looking at this and I can run through my test. It's not geometric. I can't use the nth term test. So direct comparison test looks pretty good. And I think I'm going to compare with a p-series. Let's take a look at how 1 over n cubed plus 1 is going to compare with maybe a p-series. I know if I take away that 1 from the denominator, that denominator will get smaller, meaning the ratio 1 over n cubed will get larger. So I have this direct comparison test here. And I know that we're positive for all values n equals 1 to infinity. So I know I can use this direct comparison test. So now I need to know, what does this do? If I consider the series from 1 to infinity of 1 over n cubed, well that will converge by p-series. And therefore, I know my series here is also going to converge by the direct comparison test. So take a minute to go through that logic and make sure that you are comfortable with it, with this direct comparison test that I used here. We're always going to be comparing to a p-series or maybe a geometric series. You want to compare with something easy. Let's take a look at my next example. Here I have the series n equals 1 to infinity of 1 over 3 raised to the n plus 1. So I'm spot checking the nth term test for divergence. That limit as n goes to infinity of a sub n is indeed 0. So I'm good to move on. It's not going to be geometric because of that plus 2. So I'm thinking a comparison. And I'm thinking a similar order comparison. So I have 1 over 3n plus 2. And if I take away that plus 2, that denominator gets smaller, so the ratio gets larger. And I have this comparison here that I can say. And again, I know 1 over 3 to the n plus 2 is always going to be positive from 1 to infinity. Same thing with 1 over 3 to the n. So I'm good to use this direct comparison test. So now I need to know what this thing's going to do. Well, that's not a p-series. However, it is geometric. If I rewrite this just a little bit, I could rewrite this as 1/3 raised to the nth power. So therefore, I know this right here is geometric with the common ratio of 1/3. Since the common ratio is less than 1, I know the series will converge. And I also know what it converges to. It's not necessary that you tell me what it converges to, but let's review that really quick. So I know that an infinite geometric series will converge to the first term. In this case, it's 1/3, all over 1 minus the common ratio, which is 1/3. So it's going to converge to 1/3 all over 2/3, which is therefore going to give me a half that it's going to converge to. Awesome. So now, since I know this, think about what you know about this series. Therefore, I know the series from 1 to infinity of 1 over 3 to the n plus 2 will also converge by direct comparison test. All right, this is important that we make a note. We do not know, like they don't converge to the same thing. Like, we don't know that. They might converge to the same thing, unlikely, but they might, but we don't know that for sure. So we certainly couldn't make any further conclusions. All right, so what I think I'd like for you guys to do now is pause the video and go ahead and give these next two examples a try. So go ahead and try and do D and E on your own, and then whenever you're finished, unpause the video and check your work and see if we had the same approach. Okay, welcome back. Hopefully you didn't have too much trouble and you're confident with what you've done for D and E. So let's go ahead and go over them. Remember, just like comparison test back from chapter 8 when we did improper integrals, you and I may do it a different way, and we both could be perfectly right. You have options here. So it's important that you show all your work and that I can tell your logic. So first, I am spot checking that the limit as n approaches infinity of a sub n is equal to 0, which it is. Now I'm taking a look, and I'm seeing a problem right off the bat. So if I'm starting at 1 right here, this right here, if I plug in a 1, I would get a negative number down here. And that would happen, I would be negative from 1 to 2. So right now, as this is written, the direct comparison test cannot be used. I'm not sure if anyone caught that or not, but as this is written, the direct comparison test actually couldn't be used. I don't think that was intentional. Pretty sure this is an oversight on my part. So we're going to change this up a little bit, and let's consider the sequence starting at 2. So if you didn't catch that and you weren't thinking about that positive part, something to put on our radar. And let's just change this, change that 1 to a 2, and let's consider the sequence. So my limit as n approaches infinity of a sub n does equal 0. I'm good to go from there. This thing might converge, but I don't know for sure. So let's think about what I start with here. Since I'm subtracting the 2, if I take that away, that actually makes my denominator larger. So when I take that away, if the denominator gets larger, that means the ratio is getting smaller. So here I can make this comparison and say that is true in my region. And now I need to know, well, let's consider this one. What does this do? And I notice this is going to be another p-series. If I take a look here, I could rewrite this as n to the 1/2. So my p is a half. Therefore, the series will diverge by p-series. Therefore, I know this original series, again I've changed this to 2 to infinity, of 1 over the square root of n minus 2 will diverge by direct comparison test. All right, let's take a look at the last one, E. All right, so I have the series n equals 1 to infinity of cosine of n all over 2n. So building a comparison is tough here. However, I am working with that cosine. So I know that cosine sits between -1 and 1. Actually, I can include those negative ones and the ones. Now if I divide everything by 2 raised to the n, I have -1 over 2 to the n is less than or equal to cosine of n all over 2 to the n, which is less than or equal to 1 over 2 to the n. And so you have two different comparisons you could possibly work with. You could work with this comparison, and if you're working with this comparison, it's really only useful if this piece diverges. Or you could work with this comparison, and that comparison, again, is only going to be useful if this one converges. So I'm taking a look, both of these are geometric series, and they both converge because they're going to have a common ratio of a half here in the yellow or a -1/2 here in the red. And so therefore I'm going to conclude, I'm going to use this comparison right here. Cosine of n over 2 to the n is less than or equal to 1 over 2 to the n. So now what I need to do is I need to conclude, well, what does the sum from n equals 1 to infinity of 1 over 2 to the n do? If you need to rewrite this to see it as 1/2 raised to the n, so you can see this is geometric with a common ratio of a half, and since that's less than 1, the series will converge. And again, you can tell me what it converges to here. It's going to converge to the first term, which is a half, all over 1 minus a half. So I just get a half over a half, which is 1. Not necessary to tell me what it converges to, but it's exciting that we can find that. And then, therefore, I know my original series. Will also converge by direct comparison test. So that is my direct comparison test, and we've got 5 different examples here, so that's a lot to work with. Now I would like to switch gears and review the limit comparison test. So remember that the direct comparison test, the order matters. Whichever series, I should say sequence, is bigger or smaller matters. But with a limit comparison test, it's not going to matter so much. So let's review the limit comparison test. It says if you have a sub n is greater than or equal to 0 and b sub n is greater than or equal to 0, again, we're looking at positive sequences, although they can be equal to 0. And the limit as n approaches infinity of a sub n over b sub n equals L, or the limit as n approaches infinity of b sub n over a sub n equals L. So notice it doesn't matter which series is in your numerator or denominator. They just have to equal a limit where that limit L is both positive and finite. Then the two series either both converge or both diverge. So when you're building your comparison with a limit comparison test, think about comparing with just something easy, usually a p-series or a geometric series, something that you know what it does. Now let's look at some examples. So here in the first example, I have the sum from n equals 1 to infinity of 1 over this quadratic. And so what I'm going to do is I'm going to compare with a p-series, and I'm just going to choose 1 over n squared. And the reason I'm choosing 1 over n squared is because of this dominating power down here. So once I choose to compare it, I might as well go ahead and note that I know this series is going to converge by p-series. So next what I'm going to do is I got to determine what is the limit as n approaches infinity of a sub n, I'm going to call a sub n my original, over b sub n, I'm going to call b sub n my comparison. But remember, the order does not matter. You could have put the 1 over n squared in the numerator if you'd wanted. So when I clean this up, I have n squared over 3n squared minus 4n plus 5, giving me a 1/3. And that 1/3 is both finite and positive, so I'm good to go. I now have everything I need to prove that the sum from n equals 1 to infinity of 1 over 3n squared minus 4n plus 5 will converge, and this time by the LCT, the limit comparison test. So you needed a few things. You needed to make sure you outlined, let's go piece by piece. You had to outline your comparison and tell me what your comparison does. Then you have to prove your limit, and then you have to make your conclusion statement. So we're really looking at 4 different elements using that LCT. Let's take a look at part B. So here, when I'm looking at my a sub n, and I'm thinking of a comparison, if I take those dominating powers, n to the 4th over 4n to the 5th, and I divide them, I would get 1 over 4n. So when I'm thinking about what I'm going to compare with, I'm going to compare with the series from n equals 1 to infinity of 1 over 4n, but you know, I'm just going to ditch this 4, and I'm just going to compare with the series from n equals 1 to infinity of 1 over n, because that constant isn't going to do anything. Now what I want to do is I want to note, what does this series do? And go ahead and cross that out. That's like my side work. This one is going to be diverging, so it's going to diverge, and that's by p-series. And now I'm ready to tackle my limit. So I need to take the limit as n approaches infinity of n to the 4th plus 10 all over 4n to the 5th minus n cubed plus 7 all over 1 over n. When I multiply these out, you know, I would take that n and it would be multiplied in that numerator, so I'd have n to the 5th plus 10n, making sure that I distribute it to everything, over 4n to the 5th minus n cubed plus 7. And here I would get a 4th. And 1/4 is both finite and positive. Therefore, my series, n equals 1 to infinity, of n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7 will diverge by direct comparison test. So now I think you know the drill. I have 2 more examples here. I'd like you to pause the video, work the next 2 problems on your own, C and D, and when you're done and you have all of your work shown, then you can come back and watch me work through those examples to make sure that we are all set. So go ahead and pause now. Welcome back. I hope that you had no issues with these next 2 problems. I'm going to run through my solutions really quickly so that you can verify your answers and solidify your understanding. When I'm looking at this first one, I have the sum from n equals 2 to infinity of 1 over n cubed minus 2. I'm going to use a limit comparison test, and I'm going to compare with the sum from n equals 2 to infinity of 1 over n cubed. And this is a nice and easy one to compare with because I know this one is going to converge by p-series, with that p-value being 3. And I want to make a note that you might really want to use that direct comparison test for whatever reason. It's a fan favorite and people tend to like it more. But because of this minus 2, you're going to have an issue with it, because if I try and compare with 1 over n cubed, it will be less than 1 over n cubed minus 2. And since I know this series is going to converge here, it's just not helpful. So a direct comparison test is not going to be the way to go here. It's true, but it's just not helpful. Oh wow, could I spell? It would be helpful if I could spell. Helpful. All right, so moving on with my limit comparison test, because it's going to be easy peasy. I have my comparison. I know that the series I'm going to compare with converges. Last step is I have to take a look at that limit as n approaches infinity of 1 over n cubed minus 2 over 1 over n cubed. And I need to prove that this is finite and positive. So cleaning this up, I get n cubed over n cubed minus 2, and the limit as n approaches infinity is 1. And since that's finite and positive, I therefore can conclude that the sum from n equals 2 to infinity of 1 over n cubed minus 2 will converge by the limit comparison test. All right, one more to go. So here I have the sum from n equals 1 to infinity of 1 over the square root of 3n minus 2. So I'm going to choose to compare with the sum from n equals 1 to infinity of 1 over the square root of n. And I know that this will diverge by p series, because my p is a half. So now all I've got to do is prove that my limit as n approaches infinity of 1 over the square root of 3n minus 2 over 1 over the square root of n is finite and positive. And then I'll be done. When I clean this up, I get the square root of n over the square root of 3n minus 2. And at this point, I'm kind of a little stuck. I can go ahead and say this is equal to infinity over infinity if I want to, and I can use a L'Hopital rule there, and I'm sure it would all work out just fine. But I want to show you a little trick of just an easy switch right here. Let's do the limit as n approaches infinity of 1 over the square root of n over 1 over the square root of 3n minus 2 instead. Remember, that order doesn't matter. What this does is it puts that square root of 3n minus 2 in my numerator. And now algebraically, I can clean this up to 3n minus 2 over an n. And since I have that difference in the numerator now, this just becomes the square root of 3n over n, which is just a 3, minus a 2 over n. And now as n approaches infinity, this 2 over n, well, this piece just goes to 0, and I'm just left with the square root of 3. And the square root of 3 is both finite and positive. Therefore, the series n equals 1 to infinity of 1 over the square root of 3n minus 2 will diverge by my LCT. So it's not that I couldn't do this limit up here that I have written in black. I could have pursued that. I could have rewritten this using my properties of radicals as n over 3n minus 2. But at that point, because of that difference in the denominator, I couldn't have cleaned up that radicand at all, and I think L'Hopital rule was going to be my only option there. But just by a simple switch, that cleaned up my algebra. All right, so I hope you're feeling good about the direct comparison test and the limit comparison test. And just to give you a look at what's coming up next, we have 2 more parts. In 9.4 part 5, we're going to talk about the alternating series test and then a definition of conditional convergence that's going to come with that. So only one more test in that next section. And then in that last section, we have our ratio test, which is probably going to be our most important. Arguably, probably nth term test for divergence and ratio test are going to be our most important, and then our root test. And so we're almost done, and I'll see you guys next time.